Okay, so I wanted to show you a graph of our inverses, and if you'll see, one is in green, one is in blue, you're going to notice that they are symmetrical to each other about the line y equal to x, which, if you recall, a line y equal to x is 1x plus 0. It's the parent graph of the linear function, and this is it right here, that line right there. And if you were to flip that line up here over the invisible y equal to x, you would overlap on top of your inverse. So that's one way to check to see if your two equations are inverses. They should be symmetrical. Another way is to do what we call composition of functions. And composition of functions, you'll see a little circle between the two letters. That's what it means. And basically all you're doing is that you're going to place the g function into the f function. Okay? And when that occurs, if the two equations are inverses, you're going to end up with the equation y equal to x. So basically everything's going to cancel itself out and you'll end up back at y equal to x, which kind of makes sense looking at what we just saw a minute ago. So what I'm going to do is I'm going to take my g function, which is 1/5 x minus 2, and I'm going to place it into x right here. Okay, and I'm just going to rewrite it. 5 times, all of this is going in for x, so it's 1/5 x minus 2 plus 10. I still have a plus 10 there. And I'm just going to calculate that, okay? Use my distributive property. What happens to 5 when you multiply it to 1/5? Well, it cancels out. You're left with 1x. 5 times negative 2 is negative 10 plus 10. And if you notice, we're left with 1x or x. So these two are inverses of each other, okay? If I were to try another example, maybe they wouldn't be inverses of each other. I'll show you another one. Okay, so we're going to see if these two are inverses of each other. They actually don't look like they are, but we're going to verify. Now, I'm again going to place g of x into f of x. You can do it the opposite way if you'd rather. You can place f of x into g of x. That would work too. But I'm just going to keep it like I did last time. And I'm going to take g of x and place it into f of x. So when I do that, I'm going to have 3 times 1/3 x plus 4 minus 3. Okay, so all I did there is I placed g of x in for x. Okay, I've placed g of x in for f of x. I'm going to distribute. Now, again, that 3 is going to cancel, leaving you 1x, which is great. You're also going to have 3 times 4, so that's going to give you 12. And 12 minus 3 does not cancel out. And so we do not end up with y equal to x or f of x equal to x, however you want to say it. We end up with x plus 9. So this is indicative of them not being inverse of each other. Okay, just like we thought. Okay, so just to summarize what we learned today, we can take ordered pairs, flip them around to find inverses. So if I were to do that with this example, I would end up with 1, 2, 4, 3, 7, negative 5. I can take equations to figure out if they are inverses. If I want to find out if an equation is an inverse, or if I want to find an inverse, I simply take y and x, switch them out, take my new equation, and solve for y. In this case, they are inverses of each other. If I were to graph those, they would be reflected over y equal x. And then the other thing we can do is that we can do composition of functions that we did a little while ago, where we place the function into the other function. If that happens, everything should cancel out and you should be left with x. If you're not left with x, then you do not have inverse functions.